Good morning, MTE 203. So, I hope you all have a happy engineer day and all that good stuff. Hope you have a fair bit of fun. Try to keep this lecture on the shorter end just so that you don't have to sit in front of the computer for a really long time doing all this stuff. You can pause the video anytime you want. I'll give you a warning before I scroll on to new material so that you can pause it if you want to take your notes, all that good stuff. But let's get to it. So last lecture, we talked about finding volumes of revolution, right? And now our goal is to talk about centers of mass and centers of inertia, with really the main focus will be on the center of mass, which is a particular type of center of inertia. So let's view the Calc 1 problem that you should have seen before, but again, if you haven't, it's not a big deal. We're going to cover it now. So consider an object that I have kind of something that looks like this, right? The thing I care about is this thin plate here. And a natural question I could ask would be, what is the center of mass of the plate, right? Before you even get to that, the natural question is, what is even a center of mass? Well, basically, if you thought of this as a literal thin plate, the center of mass would be some point over here that if you balanced it at that point on your finger, then it would just stay at that point, right? All the forces are nicely balanced. So from Calc 1, we have a few classic formulas for driving center of mass, but these formulas require the density to be constant, which is something that we'll address later. So here are the way that I need to compute the center of mass. The first thing I have to do is compute the total mass. So if I wanted to compute the total mass of a plate like this, well, you can just imagine we take this little thing here, we split it up into little squares, little cubes, right? So do this kind of a split up. Then I want to compute how much stuff is in each one of these little squares. And the way I do that would just be kind of integration, right? So how much stuff is in kind of this little rectangle? Well, it's going to be the height of the rectangle, so in this case, f of x minus g of x, multiplied by the width, in that case, my delta x or my dx, if I take it in the limit. And then from here, I need to multiply that by the density, so I can get basically the density times the area will tell me approximately the mass, right? Now, if I take this in the limit and I integrate this from a to b, the two edges, this tells me the exact mass, okay? So this formula is just the formula that I have down here, and it's just something that you should have already known, but if not, it's not a big deal. It's kind of natural to think, hey, if it has a constant density, then the mass will be density times area. And that's all this formula does here. Okay, so now I'm going to go over and talk about the next equation down here. So if you want, just pause the video and look at the stuff. Okay, now that I have the mass of the plate, in order to compute the center of mass, basically what I want to do, if I just do this in the x direction, is I want to find the line right here, or wherever it is, such that the mass on this half of the line is the same as the mass on this half of the line. The classic analogy that's used here is if I have a little teeter-totter, right? Just imagine I have some humans or cats or whatever on here. These have different weights, right? And they're at different locations. To find the center of mass, I want to find a point here such that the forces from these humans balance the forces from the other humans, right? I want it to balance. That's essentially what the center of mass does. So in order for this to balance, just kind of recall from your real life, real world examples, if I put a mass all the way over here, right, this mass has more of an impact than if I were to pick up this mass and say place it over here instead, right? So the distance that I am from the center matters. So if I call this point here x bar, for being the average is the idea, and I call this distance x, and I call the mass of this object m, the contribution that this term has to the whole total thing will be m times x, right? And my goal is to try to get the masses to balance off either side. Okay. So here in this case, basically what I would do is I would add up the terms on this side, so there's 3 of them, so just say I is equal to 1, 3, of each one of these masses times each one of these distances. And that would have to balance the mass on this side. So again, from I is equal to 1, I'm going to put another dot just my formula is different, to 4 of m, in this case I'll call it j and call this a j, just to keep the masses different, xj. Okay, so I want these 2 terms to balance. Okay, now this formula is not particularly useful because within these xi's, I have this unknown x bar floating around, right? So what we end up doing to get something that's a little less conceptual maybe, but more useful in practice, is based off this picture here, I define some coordinate system. So let's see if it lets me change our color. There we go. So I define some coordinate system where I say x is 0 is maybe here, right? And based off this coordinate system, my center of mass would be over here at x bar. And each one of these terms has its new term that I'm going to call xi. I'll call it ai, just to make it different, right? It's not this xi, but it's a new distance from some coordinate system. So here, if I want all the forces to balance, what I'm going to now have is the sum from I is equal to 1 up to 7. So I'm going to add up all of these points of the masses of each point multiplied by the amount of force difference that I have, right? So this is going to be the AI position minus my x bar position. And this all should be 0 if I want the forces to balance out at x bar, right? So I don't know what x bar is. It is an unknown. I want to know x bar, right? But I have one center of mass. It's right here. And at the center of mass, all the forces will balance because this will just kind of, if I put my finger there, it'll stay balanced up. So now I want to solve this thing for x. So from here, if I do the magic of just a little bit of algebra, I could take this whole thing, I solve for x, and I get x is equal to, well here, I have this whole sum, right? So I add up all the masses in front of x. So I'm going to have 1 over the total mass, right? Because if I add up all the masses, I get the total mass. And this is going to be, well, pull the x out, and then I'm just going to have the sum from I is equal to 1 to 7 of mi times this distance ai, where again, this distance ai is now from 0, right? It's from whatever my coordinate system was chosen to be, right? So if I change the coordinate system, if I move this point, right, if I move that point all the way over to here, right, this formula gets tweaked, right? But the answer will always be the same when I chase it out, right? Because it's just forcing the forces to be balanced. Okay, so this is the idea of how it works in the finite world, a finite number of point masses. When I put all this together, I end up with this formula down here. And I'll pause the video if you want. Okay, so I end up with this formula here, right? In the limit, the mass, so here I had 1 over mass, if I just pull the mass over to this side, times this point, like my center of mass, is going to be equal to the integral from a to b, like add up all the masses, right? The sum would turn into an integral from a to b, in this case because of these guys, of x, that's the distance that I care about, that's my a in this case, times the contribution of the mass. Well, the contribution of the mass in this case, I'd want to integrate these little bitty rectangles, right? So I want to integrate the density times this term here, right? That tells me the height of the rectangle, the instantaneous mass, if you want. Okay. Now, in y, I would do a similar formula, but there's kind of a problem with how this problem is set up, right? I want to compute the center if I go kind of this way. The line that I put here, that it would be even across that line, right? So the problem here is basically just tied to our coordinate system a little bit. So if I want to do this with a single integral, I need to talk about kind of, well, how much of a weighing I have between the mass for any given slice. And to account for that, I take the same formula that I had here with this piece here telling me the amount of mass along a line, right? And this is my new metric for how far away I am from the y-axis. So instead of just talking about the distance x, which I could do here because I had nice even slices this way, since I now have a curve in the y direction, I need to take the average. Okay. Hand wavy excuse for why that formula comes out to be the way it is, but in practice, we're not going to use these formulas. We're going to use the Calc 2 version of the formulas, or Calc 3 version, that don't have this problem of doing the weird thing for y, and you'll see after we do a problem why this comes out to be the way it is, right? So in Calc 2 version, we don't have to do weird things. Our formulas will always look kind of like this. Now, since this is titled center of gravity and moment of inertia, right? Where's the moment of inertia? Well, we call this thing the first moment of inertia of mass. Okay, just a fancy way of talking about how forces would be applied to this object, right? If I apply a force at the center of mass, it just moves the object. If you imagine I push on this edge, it would rotate the object around. That's what that idea of this moment of inertia is trying to capture. Okay, so let's look at some questions now. And by questions, I mean let's first generalize this. So if I wanted to do this in 2 dimensions, so I now have an object that looks just like what I had before, right? In theory, I could have some big blob object like this. Sorry, that got cut out. Let's just do there, right? And I wanted to know, hey, this thing has a variable density, rho x comma y. How much does it weigh? Yeah, natural question to ask. Well, the total weight is just going to be the double integral of the density function with respect to my dA, right? If I wanted to do it in 3D, I would just do the triple integral of dV, right? Nothing really changes there. If I want to know the moment of inertia, this top formula captures all the key ideas, right? But now it's just going to be the double integral of x. So if I want the center of mass in the x direction, right? I want the mass on this half to balance the mass on that half. So it's just going to be x, the distance from whatever coordinate system I decide to use, times my density function, just double integrate that. For y, if I go here, by symmetry, it's just going to be the same formula, right? This inner integral, this term here, right? This and the dy that's associated with it. This is the term that I was struggling to compute over here to figure out what this thing was, right? I need to find out what the limits of the inner integral were. And over here, this term that's under this underbrace with the y, that term is basically going to be what comes out when I do these limits over here, right? In these cases, rho was a constant, so rho doesn't matter. It's just trying to figure out what these terms are, right? So that was the struggle that I had for the Calc 1 version, but now, just like with volumes of revolution, the double integration handles all the hard stuff. Okay, so now if I want to build the center of mass, my formulas stay the same, right? So the formulas are just moment of inertia is equal to moment of inertia, right? At that point, I'm at what I call the center of mass. So at that point, again, it just balances on my finger. Okay, so here you get the same formula that I had over here, right? But I just get this nice term here. Okay, so that's it, right? If I ever ask you to compute a moment of inertia, what I'm asking you to do is to compute one of these, right? Well, if the first moment of inertia. If I ever ask you to compute the center of mass, you need to compute the mass, the moment of inertia, well, both of them, and then you need to solve this equation for x bar and y bar. That's it. That's what I'm going to give you to do with this. So fundamentally, it's nothing really new. It's just set up the integrals and do it. So let's go through some examples real quick and just chase it out. Oh yeah, one other comment. In higher dimensions, this generalizes in the natural way. By the natural way, I mean I would get triple integrals and here I would have a z. The dA, I would call it dV for volume. Here, I would still have an x in a y in an x moment of inertia, but I'd also have a third term that tells me what's happening with z, right? So I'd have a double integral, and I want to talk about the distance from the z-axis, so I'd have my z, p, x, y, z sitting here, right? And if I wanted to compute this, I would have mz bar is equal to that to chase that out, right? That would be it. Okay. Nice and easy, generalizes the natural way, all that good stuff. Okay. So, find the center of mass of a thin, so by thin I mean essentially two-dimensional, plate with constant mass m if its edges are defined by these two curves. Okay, so what I need to do here is set up my double integral and then evaluate it. So how do we go about setting up double integrals? Again, the first thing we always do is we draw our picture so we have an idea of what we're talking about. So if I look at these two curves here, I know the roots are going to be 2 would work and 0 would work, right? So this goes through the point 0 and it goes through the point over here 2. And I know, because I have a negative x squared, it opens something like this, right? It looks, oops, let's draw it a little cleaner. I know it looks something like that. Okay, pause, I'm going to redraw it. Okay, so now what does this equation look like? Well, the roots will be 2 and negative 2. So I'm going to have a root here, and I'm going to have a root all the way over here at minus 2. And this one opens up. So it's got to look something like this, where it comes through here. Okay. So the region that I care about is the region between the middle of these, so I want to know what the center of mass of this thing is, where this has a constant density rho. So I'm going to have to integrate a bunch of things, so let's set up the region. So to do this, I need to know, again, what the upper curve and lower curves are for both x and y, and for one of these values, I'm going to need, well, if I do it for y first, I have the same curves, right? Red's always the top one, blue's always the bottom one. If I did it the other direction, the top one, well, it'd be along here, right? So the top would be this, bottom would be this. Then here it would change, right? The top would be this other curve. So let's not do x, right? So I'm going to integrate y first, and then x. So I'll set up the one for mass. So mass will be, again, the double integral over this region R of just rho dA. That's it, okay? That's the physics we need to know. Memorize the formula if you want, will. So this will be an iterated integral, right? The function's nice, the region's nice, we can do this. dy dx. And here I'm going to have a rho. Okay. Now I need to ask, what's the smallest y can be? What's the curve that bounds y? Well, it's going to be the one that is in blue here, this term, right? So I know y is at a minimum x squared minus 4, and at a maximum 2x minus x squared. Okay. Now that I've integrated that, again, basically I'm projecting this so it's flattened. So I have a region from this point over here, all the stuff in the middle, over to here. This is the function I want to integrate, and I need to know what its lowest x and highest x are. So know the highest x, well, both of these have a root of 2. That's going to be 2. But for the minimum one, I need to solve this equation. So I end up getting this point is going to be the point such that these two equations match. So 2x minus x squared has to be equal to x squared minus 4. So if I take this and add the x squared, I'm going to get 2x squared, subtract this, minus 2x, add, or leave that alone, minus 4 is equal to 0, right? So just adding this to the side, subtracting that. So here everything has a 2, so this is the same thing as x squared minus x minus 2 is equal to 0, and I want to find the roots. So use your favorite method. If you look at it, it's, hey, that's going to be x minus 2, x plus 1 is equal to 0, and I want this point over here. So this first root tells me, hey, they match at 2. I already knew that. This other one says, hey, they match at -1. So my bottom limit will be a -1. Okay, so that's the stuff that you'd have to generally do to find where the two curves intersect. Just make sure you pick the right curves. That's probably my #1 error, is grabbing the wrong curve, right? I think we all know that by now. Okay, so this is the mass. Okay, now to find the center of mass, I need the first moment of inertia, this mx bar, to be equal to the first moment of inertia, so that's going to be my integral of the thing where I put x in the integrand. Okay, so what I'm going to do is I'm going to erase this stuff. So if you want it, pause the video now. Okay, and I'll just put a -1 here because I want to give you guys a copy of this as the solutions. Anyways, now I need to compute this thing where mx bar is going to be equal to the double integral of, well, now since I just want it in the x direction first, it's going to be the distance x times my function rho dy dx. Now, these integrands, or sorry, the limits for these integrals will be the same. X squared minus 4, 2x minus x squared. And the reason why these are the same is I didn't change anything, right? I'm just changing my function, changing the integrand, the thing I'm integrating. These stay the same. So for these problems, you just have to set up these once, and then in theory, you're good to go. What can happen is, unfortunately, sometimes it might be that you can't integrate the new resulting function, in which case you might want to switch coordinate systems, do some of that newer stuff that we've been playing with. Okay, so through the magic of just integrating this, I get equals some intermediary steps that you should go through to compute, and this will ultimately be equal to 9 rho over 2. All right, this is a standard integral. You should be able to just chase it out. Just do the thing. Okay, so since I have this, my original mass, which I didn't compute over here, but I'll place it here, was 9 rho. Right, so I should have highlighted this guy. So to have 9 rho times x bar is equal to this, solve for x bar, and I get x bar is equal to 9 rho over 2 divided by 9 rho. This whole thing is just a half. So my center of mass is, if I take over here, take this little half step. If I put my hand anywhere along this line, it would be balanced in the x direction, right? There's one particular spot somewhere in here where it's also balanced in the y direction, right? But this tells me the x term. Okay. So now I need to do the other center of mass as well, and we'll just write it here. So to compute the other one, I still need the mass times y bar is equal to, my integral will stay the same, like the limits will, not the integral itself. So I get x squared minus 4, 2x minus x squared. Here I get y rho dy dx, right? And here, if I evaluate this thing, it becomes, let's see what I had over here, it becomes minus 27 rho over 2. And from here, divide again by the mass. This tells me y bar is just going to be equal to minus 3 over 2. The rows cancel, right? So that's all I get there. And here, the rows will always cancel because the units have to match, and rho does not have the appropriate units for length. So that's a sanity check if I give you one of these ones with constant setups. So that's how to do it, right? It's just setting these up, setting up the integral, and doing it. Right? We've had practice with that. Let's see something a little bit different. So here, find the first moment of area about this line. What's a moment of area? Well, it's basically the same idea as what I had for the setup of moment of mass, but now I'm just saying that, hey, the density is just 1, right? So I just care about the area, right? Here, when I care about total mass, I integrate density. If I want to talk about area and moment of area and these kind of ideas, it's really just the moment of, the center of, moment of mass where the mass function is a constant. So it's just a fancy way of saying, hey, find these things where rho is 1. That's it. Okay? So that's all it's asking. And if I were to ask you something like this, I wouldn't phrase it like this. I'd just say moment of mass and say, like, hey, the math, like, rho is 7 or whatever, just so that you don't have to memorize this extra terminology. But this is a good problem for setting up another integral, so that's why we're going to do it here. Okay, so like always, the first thing I have to do is understand what my thing looks like, because if you don't know what it looks like, have fun setting up the limits. Okay, so I'm told I'm bounded by this function and this function. Okay, so what do these things look like? Well, x is equal to 2 minus y squared. That's going to be a parabola opening up in this direction, right? Because it's along the y-axis. So that thing is going to look like this. Something like this, right? And I know it's going to be centered here on the x-axis just because the roots of this are going to be plus or minus square root 2, right? Okay, now this x is equal to y absolute value of that thing cubed. If you think about it for a little bit, well, 0, 0 is a point on it, right? And if I make x some value here, there's two different values of y that would work for it, right? Like if x is 1, y is plus or minus 1. So this also has like a nice symmetry, and it kind of looks like this. Whatever I do here, I do at this bottom. So I get something like this. And I have this point here that I don't know, and I have this point here that I don't know. So here, the weird part of this question is that I'm not asking you to find the center of mass, right? I'm asking you to find the moment about a line, okay? This is just like the things that we did with the rotational stuff, where all I'm doing is I'm really just changing where I'm asking you to rotate it about, right? Now I'm just asking, hey, what's this moment with respect to this line over here? I'm telling you what the axis is. So this line, okay, don't want to do that. So this line, y is equal to minus 2, is going to be somewhere down here. But before we start talking about that, let's just kind of figure out what's going on with this picture. This point here is where these two things cross, right? And if you look at it for a little bit of time, you can figure out that this point will be 1, 1, right? So if x is equal to 1, right, then if y is equal to 1 and y is equal to 1, these match, or just solve the system of equations. And this point will be 0.1 minus 1. Okay. So with this in mind, I care about the moment of area of this thing, which is kind of like the center of mass, but again, I'm doing it off kilter, so it's a little bit different. So from here, I want to rotate about the line y is equal to minus 2. Not rotate, but I want to compute everything amongst that. So the only thing that changes here is I'm going to have the double integral over my region R of moment of area, so I'm just going to have 1 times this distance, right? Now if I just said across the y-axis, it would be 0, or sorry, it would be y, because I have a center at 0. But now since I'm asking this, I need to really ask, what's the distance from a point in this region to this line here? And that distance will just be y plus 2. So this is how I get the moment of area that I want in particular. And this will be dA. Okay? So all this question is asking me to do is to evaluate this integral. Okay? Again, we didn't really talk about first moments of area, that kind of thing, but this is how it works. This is what it is, right? Okay, so if I want to integrate this, what do I do? Well, I have to set up the integral, right? So that gives me the choice. Do I want to integrate with respect to x first, or do I want to integrate with respect to y first? So if I look at it, the nice option to pick is x, because the curves don't change. It's the same lower bound, it's the same upper bound, right? But if I picked y, I kept that one there. But if I picked y, then the functions change as they go about, right? So let's not do that to try to avoid it as much as we can, at least. So how do I chase this out? So I'm going to get the integral of my y plus 2 dx dA, or sorry, dy. So the inner integral, the bottom limit will be this curve, right? And this curve was the parabola that opened that way. That's my absolute value of y to the third. So I'm just going to put this in here, y to the third. And the upper bound will be 2 minus y squared. Now, when I integrate this for y, I kind of run into a little bit of a problem, right? Depending on the value of y, if y is over here versus this region here, this absolute value of y cubed changes whether it's positive or negative, right? So that's a problem here. So I actually can't integrate this in one integral because this bottom limit changes. Like there's some things you can do to try to make that argument of how you can make it work there, but generally the easiest way is to not say absolute value of y cubed here, but to split it up based off of the value of y. So what I could do is I could just say, hey, if I'm down here, if I'm between minus 1 and 0, that absolute value of y cubed is just going to be negative y cubed. And if I'm at the other part, if I'm at from 0 to 1, the bottom integral will be y cubed, right? Because the sign of the absolute value of y needs to always be positive, but the sign of my y is changing, so I get that. And I get my dx, my dy. Okay, so this is the thing I have to integrate. I will trust you to be able to integrate it. When I do it, I get this is equal to 17 over 3. So that's the final answer. And again, this is just kind of generalizing the moment of, the center of mass, right? Just moment of area instead. Actually, it's technically like the moment of inertia, not moment of mass, but yeah, that's the right idea. Okay, so we're going to look at one more problem that we'll just set up real quick. I know we're kind of running longer than I hoped we would go, so let's just look at the one more problem, then we'll be done for the day. Okay, some students I've noticed have struggled with word problems, so let's give a word-ish problem. You're designing a rocket and wish to compute the center of mass to make sure that it'll be stable throughout its 2-time unit flight. So what this is really kind of telling you here, right, this term is telling me t ranges between, say, 0 and 2, right? It's just saying it goes over 2-time units. I'm going to say 0 to 2. That's what it was intended. So that's how to interpret that guy. The main body of the rocket is a cylinder defined by x squared plus y squared is 1 for these values of z. And the cone of the rocket's given by a top half of a sphere, this sphere, for those values of z. The mass density function throughout the flight varies off of space and time, right? It's a rocket, it's burning up fuel, and it's given by this function here, right? And here I say explicitly time goes from 0 to 2. Set up the integrals to compute the center of mass as a function of time. We're not going to actually evaluate these, but I have to understand what this thing looks like. So let's notice something here. It's a cylinder and a sphere. Those are symmetric, right? So what I'm going to do is, in my plot, I'm going to look at z as a function of, say, x or y. It doesn't matter, the picture would look the same. So what does my cylinder look like? So the cylinder, like the projection of the cylinder onto here, well, if I give you values of z, it's just constant for x and y, right? So what's the biggest x or y could be? Well, it's 1 and negative 1. So this looks like something that's a region like this, where this is 1, negative 1. Everything in the middle, all this stuff, is stuff that's inside my rocket. And I go from z is 0 up to this line here at z is equal to 2. So that's the body of the rocket. Now at the top, I have a sphere that's been shifted up by 2. All right, so I have a sphere cap like this, right? And that's my top of my rocket, okay? So that's generally what my thing would look like here. Okay, so now on this region, I have a density that changes. So if I think about this function, right? If t is 0, this whole thing just simplifies to 2 times this term, right? And as t increases, all this is doing, because it's a heaviside function, is I have this kind of, in this direction, I have something that kind of looks like this, right? That's this term. Then the amplitude of it, basically in this way, kind of goes like this, and then it just drops to some value, right? So basically I'm using up my fuel as I go. So if you want just stronger visualizations over here, I've done this in MATLAB. There we go. This is what the thing looks like, right? So this is at time is 0, so x and z. As time goes up, I use up my fuel, and this sharp transition as it goes here, and at the end I stop at this point. Okay, so that's the thing I want to find the center of mass of. So let's just set up the integrals. So I first need to know the total mass. Total mass will be the double integral, not double, but triple, over this region R of my rho, and I'm just going to leave it as rho, but this function goes here, times dv. So now, I want to set this up, but it's not like the cleanest integral to do. So what I'm going to do is I'm going to split it into 2 regions, R1 down here and R2 up here. I'm going to use cylindrical coordinates to work this out, and I'm going to use spherical coordinates to work this out. So this is going to be the triple integral over R1 of rho dv plus the triple integral of R2 rho dv. Okay, so if I want to do cylindrical coordinates, my rho needs to change from a function of x, y, and z into the function with my cylindrical coordinates. And my region needs to be written in terms of my theta, my r, and my height, right? So I'll give myself a little bit more space. Okay, so it's going to be triple integral of rho, and here, this rho I want to rewrite in terms of, well, actually, I'll just be explicit. So here for this rho, my x becomes r cos theta, my y becomes r sine theta, and my z stays z. My time, that's just a parameter that just sits there, right? It just sits. At the end of the day, I'm going to have a function of t, right? And here, since I'm switching to this new coordinate system, my Jacobian gives me an r dr d theta dz. Okay, now r, what is that? Well, it's just constantly at a minimum 0, right, to fill this whole thing in. And at a maximum, r gets all the way up here to 1, right? Or if we want to be more mechanical, this tells me r squared is equal to 1 as my upper limit, so r is 1. Theta, I want to go all the way around, so 0 to 2 pi. And z, I want to go from the bottom up to the top. Okay, so this term is computing the integral over r1. Okay, to this, I need to add the integral over the top portion. Okay, this one's a bit messier, right? But what I can notice is at the top portion, take my MATLAB simulation again, rerun it, right? So this change where I'm using up my rocket fuel, I never actually reach the top, right? So this thing, as a just general function, doesn't really change as a function of time, right? So it's just what it is up there. So what I could do is to first fix my picture, because I realized I plotted it wrong. This is what my picture looks like, so I apologize. It's the cone is symmetric across here. I did a bad thing when I tried to do coordinate stuff to make the plot look pretty. Okay, so here I noticed this isn't a function of z, right? Just because, hey, z, this part never kicks into the cone. So I could take this whole thing and shift it down, right? So instead of integrating this at z is equal to 2 to chase it out, I can move it down to z is 0, so I can center it at the origin. It's similar to the other trick that I used, very similar to this before. So in spherical coordinates, I triple integrate this, And here I'm going to have my function of rho, theta, and phi, right? So I'm just going to call this, I'll call it x, y, z, and t, but keep in mind that I have to do the coordinate transform to theta, r, and phi, right? So just plug in these transforms into here of my coordinate terms. So in spherical coordinates, I end up with that r squared sine of phi floating around here. So I have r squared sine phi, and I'm going to have my dr, d theta, d phi. Okay, so I need to compute what these things are. Well, r, the smallest radius of a sphere such that I'm still inside the sphere, is 0, and that goes all the way up to r. It's a perfect sphere, so I don't have to worry about anything else. So here in this case, r will be a 1, right? Because radius 1, right? Going from here all the way over to here. Now, in terms of our angle theta, I want to go all the way around the circle because I want the whole half top of the circle, so 0 to pi. And here, I want to start this angle down to this angle here, right? So this angle. So at the top, my phi is cosine, right? So at the very top of it, I want 0, right? 0 would give me the top, and I want to go all the way down here to pi over 2, and that would sweep out the top part. So this is the total mass. It's a bit messy, but this thing here is the thing I need to compute to get the total mass. Okay, now that was pretty awful, right? But if I want to compute the center of mass, right, I'd say mx bar is equal to, I'll have the triple integral. So if I want it in the x direction, it's just x rho dv, right? So say x rho dv, well, x, all I do is do the coordinate transform for x for these two, solve that for x, and I get the center of mass there. I also have another one, my bar, that's over r, of, it'll be the triple integral of y bar rho dv. And this exact same trick works, right? All I do is multiply this by, y bar, all I do is multiply this by y, right? And plug that through the coordinate transform. Now for z, it's a bit annoying, but it's not horrid. I get r z rho dv. Now this second integral here, the way I set this up, was using the fact that rho doesn't effectively depend on z at the top part of the cone. Now it does. So what I would have to do there is, I could do the same transform, right? But I'd have to transform my integrand appropriately. So if I want to pull this down by 2, I'd have to subtract 2 from this, right, to do that shift. And then I just, at that point, I can do the same tricks, right? So that's how to set this up, is you just evaluate these integrals and chase it out. Not going to actually evaluate the integrals, not going to actually give you the thing, but that's how it would work, okay? So for suggested problems, I suggest doing 1 through 27 or some subset of them. Just practice setting up a few integrals. Really, if you've been practicing setting up your double integrals, right, these regions, all this is doing is multiplying by x or y or z or doing the shift thing if needed. But really, if you just care about the center of mass, just x, y, and z. It's just setting up a double integral. Thus why moving this lecture online wasn't that big of a deal, so that you guys could go enjoy your engineering day. Okay, so that is that. If you wanted, you can practice setting this up. If you want to play with my code, here it is. This stuff, I'll leave it. You can copy it. It's kind of a rough code to chase it out. The error that I had earlier is this should have had this cosine term here, and I did not include it. But yeah, so all we do is evaluate this thing, and basically, oops, I don't want to save it. Basically, our center of mass would start, so it's going to be in the middle, it's going to be at 0, right? And it's going to start somewhere slightly above 1 because of this cap, and then as it goes up, the center of mass will slide up accordingly, that kind of a thing. All right? And generally, rockets are stable if, let me see, I can draw on here. Yeah, rockets are stable if my center of mass is, higher up than my center of, down here, another center that is the center of, if you will, aerodynamics. I forgot its official name, right? So if the center of mass is higher than here, when I put a force this way to launch the rocket up, it balances out because the force that I push is acting on here, right? But the force from the air is acting on here. So if these are two off kilter, what'll happen is I could take my rocket and tilt it a little bit, and then it'll keep tilting further, right? So this is why people put fins at the bottom of the rocket, right? Because with these fins, it takes the center of inertia upon which the air is acting when it's blowing on the object. It moves it further down to the back because I have drag right here. And that drag will slow it down a little bit. Well, slow it down in the sense of it moves this center of inertia down. And the center of mass will be here, right? So obviously a potential problem with rockets is as you use up the fuel, the center of mass is moving, and you want everything to balance out so it doesn't do a SpaceX kind of thing. Okay, so there's that little fun tidbit. Enjoy your engineering day, which hopefully you're currently at now, I believe. I believe it started at 11. So yeah, enjoy all that, and I'll talk to you guys in class on Friday.